All right, so the probability that a customer selects a pizza with mushrooms will be the letter M. Pepperonis be the letter P is 0.55. The probability that a customer selects only mushrooms is 0.32. If the probability that he or she selects only pepperoni is 0.17, find the probability of the customer selecting both items. All right, I'm going to kind of show you a Venn diagram of this, make life make sense. You have two Venn diagrams. We'll call this mushrooms and we'll call this pizza, right? This guy right here, if you're straight up just mushrooms, we see is 0.32. This over here, if you're straight up just pepperonis, is 0.17. And then we saw that if you're both mushrooms and pepperonis is 0.55. Right? So here's a question. Is this mutually exclusive? Why not? Very good. You can have mushrooms and pepperoni on your pizza. So both events could happen at the same time. So if you're just trying to find the probability that he selects only, find the probability of the customer selecting both items, right? So that means they have to get mushrooms and pepperonis. So our or situation, mushrooms or pepperonis, will just be this right here. So we'll have our or situation, which you have your M and your P. But since they're mutually exclusive, I have to take away the fact that they get both mushrooms and pepperoni. All righty. So the or situation, where are we at? You know what? That 0.55 shouldn't be there. How about 6? The answer should just be 0.55. But it says mushrooms or pepperoni. So we don't actually know this number. So yeah. All right, so this 0.55 would be your or. It gives us the answer. So this is 0.55. The mushrooms here is 0.32. The pepperoni was 0.17. And we're trying to figure out what that mystery is that do mushrooms and pepperonis. And then we just kind of do some math. What's 0.32 plus 0.17? 0.49. And then what would you do next to solve this? Very good. What is 0.55 minus 0.49? 0.06. So that means you have a probability of 6% of your people that would get mushrooms and pepperoni. So that question mark there, that's not, that would just be 0.06. Go ahead, Ed, ask the question. Yeah. Those formulas to know. You just gotta know you're mutually exclusive, then you know if you're subtracting or not. Because if it is, then you don't have to subtract. If it's not, then you do have to subtract to take out that double dipping there. All right, any other questions there on 4.2? All right, let's talk about 4.3. Again, as you are working on the homeworks and stuff, if you get stuck, feel free to text me, email me. I do prefer the high school email. I don't check the Lone Star but once a day. All right, so in 4.3, we're going to talk about the multiplication rules of addition. We just did a whole bunch of adding. Those are pretty straightforward and simple. Multiplication occurs when you're trying to find out an event and then another event and then another event and so on and so on. All right, so to find the probability of compound events, we're going to use this multiplication rule. So multiplication rules can be used to find the probability of 2 or more events that occur in a sequence. So if we just wanted to see 2 things or 3 things or 4 things, we would use this situation. The events are independent, and if the probability of one is not changed by the occurrence of the first event. All right, so independent would be that one is not affected by the other. So 2 events A and B are independent. If the fact that event A occurs does not affect B. So an example here real quick is if I roll the die, and let's say I get snake eyes. If I roll the die again, does getting snake eyes the first time affect my roll the second time? No. So this is an independent situation. Now, if I'm drawing a card, a random card out of 52, and I keep it, and then I draw again, is the probability of whatever card I select the second time affected from my first card? Yes. So that would not be an independent case. So an independent case is after an event happening, it does not affect the other event happening. Now what is it? Now it's independent because again, the first one's not affecting the second one because I put the card back in. Right? Does that make sense? All right. So for instance, I guess I should really read those. It says rolling a die and getting a 5, then rolling a die and getting a 3, both independent of each other, does not affect. Drawing a card and getting a queen, replacing the card, drawing a second card and getting a queen. And again, by replacing the card, that's what keeps it independent. So questions on independent events just doesn't affect the other guy. That's what I got confused yesterday with mutually exclusive. All right, so the first multiplication rule, when two events are independent, the probability of both occurring is an and situation. So or meant what? To add. When you see an and, you're going to be multiplying. So if you want both events to happen, it is going to be an and it's going to be a multiplication problem. So the rule can be extended to 3 or more. You can do as many as you want, independent events. So I could do this 157 times and just multiply 157 probabilities. Your probability will get less and less each time, but it's definitely possible. So if a small sample is selected from a large population and the subjects are not replaced, the probability of an event occurring changes so slightly that for the most part, it is considered to remain the same. Even though the events are not independent, thus if 24% of American consumers prefer a particular brand, then if 2 Americans are selected, even without replacement, the probability that both prefer the stated brand is still going to be the same. So if our sample space is so large and you're looking at the entire country and 24% like Pepsi, and we select 2 random people in this entire country to see if they end up liking Pepsi, we're not replacing that person back into it, but technically we could say that it's also independent because the group is so large. It comes different if I ask you 6. If I ask, let's say 24% of y'all like Pepsi, and I select one person and I don't replace that, now would that be independent? No, now the sample space is so small that that percentage, y'all went from a 1/6 percentage to now a 1/5 percentage, right? So that percentage drastically changes. That's all it's stating there. So if the population is large enough, then and we're not replacing people, we don't have to worry about reducing that probability. All right, we good with that? All right. So in that example, then, if we're not worrying about it not being independent, then if I wanted to know what the probability of 2 people liking this whatever brand is, it will just be what's the probability that I select a person that likes this soda? 24%. So we'll say 0.24. If we're saying that the percentage is not changed, what's the probability that we find someone that likes this brand again? 0.24 again, right? And if we had to do this a whole bunch of times, we'd just keep multiplying the same number. So what is 0.24 times 0.24? Let's find out. Basically 24 squared. So 24, 25, 6, 25, 4 would be 596. So that'd be 5.96. No, it'd be 0.0596. 76. That was close. I had the 6. All right, so this would just be basically a 5.7% chance that you'll actually select 2 people that like this stated brand. Sorry. Any questions there? Are you able to see that blue? Do I need to make that darker? I did. Yes, sir. You're welcome. I watched a video the other night or last night. And the guy was painting this room. The wife comes in there going, "What are you doing?" He goes, "Painting the room." "Why is it, huh?" The red one, yeah. Have you seen that video? Oh, I laughed so hard. He's like, "It's olive green." He goes, "That is red." "No, no, on the can it says olive green. I'm painting olive green." "No, that's red." Like the guy was colorblind, but anyways. All right, so the probability with replacement. All right. So a jar holds 5 marbles, 5 red marbles, 3 green marbles, and 7 blue marbles. One marble is selected and its color noted. Then it is replaced. Is this an independent event? Yes, because we're replacing it. So the second event is not affected by what the first event happened. So again, a second marble then is selected and its color noted. Find the probability of each of the following happening. So let me go down a little bit. All right, so selecting green marble. So the first thing you want to do is just find your total. How many total marbles are in this jar? Right, you would just go 5 plus 3, which is 8, 8 plus 7, which is 15. Does everyone see how we get 15 as our total? So that's going to be the bottom of our fraction. So if I want the probability that 2 green marbles, my first marble must be what? Green, right? And how many green ones are there? 3. So that's going to be 3 out of 15. I examine the marble, I put it back in the jar. What's the probability that I get another green marble? Same probability, right? So 3 out of 15. After this, we're just going to straight up multiply. Now this can be simplified. What does 3/15 simplify down to? 1/5. Make your life easier if you're able to. And then how do you multiply fractions? Straight across. What's 1 times 1? 1. What's 5 times 5? 25. So you have a 1 in 25 chance that both marbles will be selected are green. Right? If you have to convert this into a decimal, by all means, yeah, just divide the 2 and you get 0.04. You good with that? All righty. On B, it says select a blue marble and notice this and here. So that means what? Multiply a green one. So what's the probability I'll get a blue one? Very good. And then what's the probability I'll get a green one? 3 out of 15, which we also note is what? 1/15. You don't have to simplify, just makes your life a little bit easier because what's 7 times 1? 7. What's 15 times 5? 75. And if you're asked to do that in a decimal form, this will just be 7 divided by 75. So you basically have a 9% chance. What was that chance again? 0.093. Repeating. Okay. Questions? All right. Part C says selecting a red marble. All right. So what's the probability that it's red? 5 out of 15. Perfect. I'll do that in the next step. Then a blue one. And again, we're told that we're replacing these back. So what's the probability that's blue? Then a green marble, which is what? Very good. 3/15 or 1/5. So if I rewrote this is just the same thing as 1/3, 7/15, and 1/5. Right? Now it makes life a little bit easier because what's 1 times 7 times 1? 7. You technically already did 5 times 15. What's 5 times 15? Then multiply that by 3 and you get 225. Right? If we needed to know the probability of that, about 3%. So 0.031 repeating. Very good. Questions on how to use the multiplication rule. All right, and that's without replacement. So let's talk about dependent events. What do you think dependent's going to mean? Very good. It's going to depend. So it's going to, whatever happens the first time is going to affect what happens the second, third, fourth, and fifth time. So when the outcome or occurrence of the first event affects the outcome or occurrence of the second event in such a way that the probability is changed, the events are dependent. Right? Questions? All right. So in example 14, it says classify events as independent or dependent. So determine which event are independent or dependent. This is a great true false question. Maybe a multi select question where it's just like independent, dependent, or whatever the answers are. So just kind of keep those in note of type of questions we could have. Part A says having a large shoe size and then having a high IQ. Independent, right? They have nothing to do with each other. So this would be independent. Independent. A parent being left-handed and having a child who is left-handed. Right. I think it's a passed down trait. So if they're left-handed, they have a higher probability of being left-handed as well, versus a right-handed parent having a left-handed child. So I think the fact that they're left-handed could affect genealogy. Yes, go ahead. I think so. I don't think so. Let's Google it. 'Cause yeah, I don't know because they say it's dependent, but I feel like this is a good argument. If it's not genetic, then technically are they independent? Uh, but it's still partially, so it's still partially affecting the outcome of the second event. So we'll go with this. So if it has to do with kids, yeah, any factors, if it affects it at all, yeah. So then on part C, so we'll go with dependent, but you'll have great arguments on that. But on part C, it says getting a raise in salary and then purchasing a new car. Does one affect the other? Absolutely, right? If I have more money, I can buy a better car. If not, I have to go with the El Junco, right? So this is dependent. Station wagon, yeah. Rolling a die and then tossing a coin. Independent have nothing to do with each other. Right? Any questions on independent or dependent? That genealogy that's gonna be an interesting one. Talking about the genealogy part. So this talks about what we talked about yesterday, where our experiences causes these opinions, right? What was that definition for? Subjective. Very good. All right. But we just Googled it. It is. Oh, and tell the. I think if you explained out your thought process, I'd probably give you credit. Yeah, for sure. I guess that's one thing that's nice about statistics is you really could argue your grade in certain situations. There's some in here that's like straight math, like standard deviation, variance, like that's a straight up answer. But some of these is like, well, subjectively, I feel this way after my experiences. So that gets a little interesting. What do you think these blanks are going to be? Conditional probability. So the conditional probability of an event B in relation to an event A is the probability that event B occurs after event A has already occurred. So this was what I was kind of talking about with the alcoholics and stuff like that. We're going to kind of get to. So if I know event A happens, what's the probability that B will happen? That's what this basically is saying. So we're not finding the probability of A and B. We're finding the probability of A actually happening and then B happening after that fact. All right. So the conditional probability of event B, given that event A occurs, is denoted with this little bar. Right. So basically, you're trying to find the probability of B happening, knowing that the event A did happen. All right. So basically, if I wanted to do the marble test, what's the probability of getting a green marble if I selected a red marble the first time and didn't replace? Right. So then that becomes a different type of probability. Right. This would be what was red at like 5 or something. This would be 5 out of 15, but then you would then multiply 3 out of 14 because we know that event happened. Right. That's basically what that's stating there. All right. So for instance, oh, well, I guess just keep reading. So for instance, if an ace has already been drawn and not replaced, then the probability that a king will be drawn, given that the ace was drawn, which is a 4 out of 50. Sorry, the ace would be it would be a 4 out of 52. And then since that event happened, picking up a king would now be 4 out of 51 because we know that we got at least an ace. So that means there's only 51 cards remaining. However, the probability of drawing an ace on the second, given the first card is an ace, is what? 3. So if we know ace was chose and we're trying to get ace again, then we know that we only have 3 aces left, but still 51 cards. Questions on conditional probability. So you're basically just trying to find the probability of the second event happening, knowing the first event. All right, so there's no multiplication here that you have to do. You're just trying to find the probability, knowing that the first event happened. All right, it should be noted. Oh, no, let's go into multiplication rule 2. Go ahead. So when 2 events are dependent, the probability of both occurring is the product of the probability of the first event and the conditional probability of the second event. Right. So if this and here is basically, all right, here's the probability of A happening, which is we do the aces, right? So we want to know the probability of both these things happening. Then we'll say this is 4 out of 52. And if we're going to grab that king, knowing the first one was an ace, I still have 4 kings, but now I only have 51 cards. And then I would multiply these out. Right. So if we're looking for a situation where we want to find the probability of getting an ace and getting a king, that's basically the math that you're doing. If you're trying to find the probability of getting a king, knowing you got an ace, then the answer would be just straight up 451, no multiplication needed. Understanding the wording there? So if it says find the probability of this given this, it's just going to be a simple fraction. If you're trying to find the probability of 2 things happening and you're not replacing, then you're going to multiply the 2 up. Good. All right. So let's look at example 15 then. So again, probability without replacement. So we'll consider a standard deck of playing cards, which again are 52 cards in a deck. 3 cards are drawn and not replaced. Find the probability of the following events. All right, so 3 cards are drawn. Right, but we're not replacing it. So what's the probability that the first one's a 10? 4 out of 52. Good, and then what's the next fraction? 3 out of 51. And then what's the probability of the next one? 2 out of 50, very good. And you just multiply those all up. You could. That would be 4 goes into a 226, 1/13. So that's 1/13. 3 does go into 51. 3 goes into it 17 times. Yeah. 51's not prime. And then 2 goes into 50 25 times. So then we could do our math a little bit easier. I would say in this situation, maybe just multiply them as is and simplifying that fraction could just be just as easy. All right, but 1 times 1 times 1 is 1. 13 times 17. Yeah, we don't got that one. All right, 221. Multiply that by 25, and we get 5525, 5,525. All right. If we then needed to turn that into a decimal, that would just be 1 divided by 5525. Ooh. All right, so that's e to the 4th. So that means I need to move that decimal 4 times to the left. So that would be 0.000. We'll just go with 1/8. So basically, that's basically stating that you have a 0.018% that you'll get 3 10s in a row. So if you get 3 of a kind, that's 0.018% that you'll get three. What's it called? 3 of a kind. Well, then that's factors that we're not playing into. We're just going to look at the what should happen versus what could happen. Right. All right, let's look at part B. Part B then says drawing a jack. What's my odds of that? 4 out of 52. Then a queen. Very good. Then a king. Very good. We're trying to go for a straight here. All right. Again, you could do all the multiplication. I'm not. I mean, all the simplification. I'm just going to straight up multiply. So 4 times 4 times 4, 64. 52 times 51 times 50. Why did I put a 30? 50. Yeah, somehow. All right, so then we'll just do the straight math from here. We'll just say 64 divided by 132, 600. And that would be 1, 2, 3, 4 eighths. All right, so if you're going for a straight this time or a high straight, then you have a 0.048% chance. So you actually have a higher probability that you'll get a high straight than you do getting a 3 of a kind, which is also, I guess, why 3 of a kind can beat a straight. The probability of it happening is less. Any questions? Maybe. Oh, I love counting cards. I just cannot do it without moving my lips. Because I can do the math and I'm like, but my lips move. And they don't kick you out, but they kick you off the table for sure. Oh no, I like the roulette table. I like the probability there. I love when people are like, they're like, all these numbers are cold. It's gonna land on this one. The probability never changes, guys. It's the same probability that that ball land on that that color and that number each time, which is just fun to me. But I like playing the probability of large numbers. If I keep betting on the same number, eventually my number will hit. So I just increase my bet as I'm losing my money, and eventually I just hope it happens sooner than later before all of my money is gone and I cannot recuperate. So that's my thought process. Most of the time. Yeah, most of the time. But there are some nights that's like, I'm just gonna go home now because I have to work 3 jobs now. So, all right, anyways, so oh my bad. All right, so drawing 3 hearts. How many hearts do we have in a suit? 13, yes, because you have the ace. Nope, you have a king. 13, yep. 13 cards in a suit. So that's 13 out of 52. What's the probability that the next one is a heart? Next one? Perfect. And we're just going to multiply that straight up. 13 times 12 times 11. 52 times 51 times 50. I did do that. I just like to do it again. I did not notice that. Oh, not an E this time. So 0.013. All right. So that basically there means that you have a 1.3% chance that you could at least get a flush, which is just the same suit. Right? Yeah, a little bit higher, but again, a flush doesn't beat a straight or a three of a kind because your probability is higher. Some people do it. All right, drawing a heart first would be 1352. A club second. That's the clover leaf looking thing. It's still going to be 13 out of 51 because we took a heart. And then a spade third. 1350. Oh, like a club two. I get it. I get it. Yeah. Because then that would just be a 1 out of 51 because there's only one club that's two. Yeah, change suits. So 13 times 13 times 13 gives us 2,197 over 132,600. I did. I just guessed it. Feel like it's right. Feel like it's getting better. So this is 0.17. Yeah, 0.017. Sorry. So I have a 1.7% chance of getting a random heart, club, and spade. And if they're not all the same number, I can't do anything with that. I just hope for a high card if you're doing a 3-card stud. That's right. So any questions on that? Multiplication rule 2, pretty straightforward. On not replacement versus replacement. All right, the next part is we're going to talk about how to find conditional probability of an event. So here we go. What do you think this first blank is going to be? Unconditional? No, it's going to be conditional. So conditional. It was. Conditional probability. So the conditional probability of an event B in relationship to event A is the probability that event B occurs after the event A has already occurred, which we've already talked about. So the formula that goes with that is the formula for, I don't know why they keep on making us write this again, but conditional probability. I think we've written this down 3 times, haven't we? I'm gonna adjust this when I teach it at the college. Is this guy right here. So basically, find the probability of both A and B happening, and then divide it from what the probability of A is, and then you can find the probability that B happens given that A happens. This formula comes into handy if that's the only thing you're given. If you're given the marble situation, it's a lot easier just to do the math yourself. But if you're not given any information and you're just told, hey, the probability of A and B happening is this percentage, probability of A is happening is this percentage, find the probability of B happens given that A. So that's what this formula right here will come into play. Right? But if you're given the scenario, just work the scenario out. This becomes a lot easier. Questions? All right. Let's look at example 16. Incarcerated population. Prison. That's like I just woke up. All right. So in a recent year, 0.99 of incarcerated population is adults, and 0.07 of the incarcerated are female. If an incarcerated person is selected at random, find the probability that the person is a female given that they're an adult. All right. So we are given this stuff right here. So for event A, being incarcerated by an adult, and event B is this right here. A and B is 0.07% because they're incarcerated are female. And the event A of happening is 0.97. So what we're going to do is to figure out the randomly chosen person is female, given that they are an adult. You're going to take the and situation, that both a female and an adult, which is 0.07, and then divide that by the actual fact that A happened, which is 0.99. So the fact that is to get an incarcerated female is 0.0707. Right? I think that says something about the females in prison. It's a low odds that you'll go to prison. Everybody see it, 7% of adults. Well, I mean, compared to what we can infer, if 7% female adults, what's the other ones? 93% males, right? Yeah. No, that was just female given that they're an adult. No. So that was the percentage that we got at the very beginning of 0.07, but we didn't know if they were adult or female. Right. All right. So the example 17 not worked out for us, so we can actually do it together. All right, so it says at a local country club, 73% of members play bridge. That's just a game. It's like it's like gin, I think, where you have to try to get them all in a row. Like, and you can pick up the stack, but you have to use it or something like that. It's an old game. All right, but a local country club, 73% of members play bridge and swim. 82% of the members play bridge. If a member is selected at random, find the probability that the member swims given that the member plays bridge. So remember that this right here, I'm trying to find the probability that the member swims given that they play bridge. So this will be my P of A. So that what goes on the bottom of my fraction. I guess it's all written out here for us. All right, so bridge plays bridge and swims is what? 73% will turn into a decimal, so 0.73. Probability that they play bridge, 0.82, very good. And if we're trying to find this, we're just going to take the probability of A, that's going to go on the bottom. So this is plays bridge, so that's 0.82. And then the plays bridge and swim, so remember it's PA on bottom, PA and B happening on top. So in this case, that would be 0.73. So what is 0.73 divided by 0.82? Yes, it's actually just 73 divided by 82, which is 0.89. So it's an 89% chance that you will select a person that swims given that they are a bridge player as well. Questions? All righty. Let's move on. So probabilities for these words that say at least, right? So the multiplication rules can be used with complementary event rules to simplify solving problems involving the word at least. So for instance, if I want to find the probability of at least one thing happening, I could just simply say 1 minus the probability of none things happening. And that would give me the same probability, right? Because at least means what? The minimum, right? That number or more. So it's the minimum value. So if I just figured out what the probability of nothing happening, I could just do 1 minus that, and that would give me the probability that it's 1 or more. All right. That's basically what they're saying. Sometimes it's easy just to calculate yourself. Sometimes it's easier. So, okay. So sometimes it's easier just to do it. And sometimes with the percentages and stuff, it's easier just to do the formula as well. So in example 18, it says at least one paid assistantship of PhD students. So 60% have paid assistantships. Basically, it's just a paid internship. If 3 students are selected at random, find the probability that at least one has a paid assistantship. All right, so. No, they're getting paid to work. Yeah, they're getting paid to work. You don't pay. You either get paid or you don't get paid to work. Yeah. Sometimes we do an internship and not get paid for it, but we're getting the experience so we can get hired. Nothing's free. It's paid somewhere. Death is free for you, not not for the rest. All right. Okay. So sorry. We're basically, we're trying to find the probability that at least one has a paid ship. So we need either 1, 2, or 3 to be paid, right? So we could find the probability that one's paid. And so I'll show you why this math becomes a little bit easier to do it this way. If I try to find the probability that at least one person gets paid, how many people? 0.60. So I would do 0.60 times 0.40 times 0.40, because at least one person would be paid. Then I would have to write that number down. Then I'd have to go find the probability that 2 people got paid. So that's 0.60 times 0.60 times 0.4. Figure out that calculation, write that number down. Then I got to go find at least 3 of them being paid. So that's going to be 0.60 times 0.60 times 0.60. Write that number down. Then add those probabilities down, right? That is what I could do the long way. Or if I'm at least doing just one, I could find out the probability that none of them get it, and then just subtract that from 1, because that's what I should be left with. So in this situation, to find none of them, all I got to do is do what? Right? So what's the probability that none of them are paid? 40. And then multiply it again, and then again. So this is one of those large samples where we don't have to worry about the replacement situation, just like we saw earlier. So that's kind of what they're going to explain here, or at least I hope, but that's what I would explain it as. So the probability of a PH student that has an assistantship is 0.60. A PH student that does not have an assistantship is, okay, none of the 3 PH students have an assistantship. How would I figure that out? 0.40 times 0.40 times 0.40. And that gives us close 0.064. It was. And then at least one of the 3 has this. I could simply just now say 1 minus none of them having it. And I get 1 minus 0.064. Something like that. Which will be 0.936. So that becomes a lot faster of a process than going over here and doing this. 0.6 times 0.4 times 0.4, getting this result. 0.6 times 0.6 times 0.4, excuse me, getting that result. 0.6 times 0.6 times 0.6, getting that result. And then adding those numbers up. And you would still get the 0.36. Do y'all believe me, or do I need to show you that? Okay. So this right here, that's why this formula comes in handy. Sometimes this way is just a lot quicker. All right. So that actually, oh no, we got one more. I thought we were done. Almost there. So an example. Example 19, at least 1 rose. So in a banquet, there are 6 roses, 9 lilies, 7 daisies, and 6 orchids. If 4 flowers are selected at random and not replaced, find the probability that at least one of the flowers is a rose, the probability that all 4 are roses, and then is either event likely to occur? Show the steps. What? Is either? Oh, either. I gotcha. Thank you. All right, so let's look at A. So the first one is the probability at least one being a flower, and we're selecting 4 flowers. So again, we could calculate getting 1 rose, getting 2 roses, getting 3 roses, getting 4 roses, adding those 4 answers up, or I could just do the what was the word? It started with a C. No, is it conditional? Well, that's what that's what it is. But what is the one where it's like the opposite? That's where my brain went. I was like, wrong class, wrong class. I got to figure out the correct verbiage here. Complementary, yes. So it's easier just to find the complementary, which is basically the event not happening. Oof. Thank you. All right, so this would be 1 minus the odds that you would not get a rose. So what's the odds that I would not get a rose? So what's the total? 22. I got 28. Is it 28? Okay. So that would be my total. So 28. And then how many of those are not roses? So I could just subtract this and then I'd be done. All right. And then that basically, oh, I apologize. That was almost too easy. So the first flower is not a rose. What's the probability that the second flower is not a rose? You're not replaced. So 21 over 27, the probability that the third one's not a rose. And then the fourth one not being. All right, now we can do the math. All right, so that's going to be what's the easiest way? Okay, I'm just going to do this one. 22 times 21 times 20 times 19. Oh, 28 times 27 times 26 times 25. All right, then I got to figure out what 175,560 divided by 491,400 is that. Yep. Oh, I could just do this -1, but it'd be a positive. So 0.643. Right. So the probability that you get at least a rose would be 64.3%. At least one rose. Makes sense. Because like I said, if we had to do this the other way, we would have to do getting one rose, no, no, no. Getting two roses, no, no. Getting three roses, no. And then getting four roses, and then adding those four results up. So that can be kind of tedious. So again, this equation comes into clutch sometimes. Sometimes it's not always the fastest one either. All right, the next one. Oh, where's that A? Aw. Oh no, that's right. Okay. B, find the probability that all four are roses. So would I want to do this math if I want them to all be four? No, just do straight up all of them being roses. So what's the probability that they're all roses the first time? What's the probability that they're all roses the second time? You're right, 5 out of 27. What's the probability that they're all roses the third time? What's the probability that they're all roses the next time? Yeah. We know the bottom number already. So now I just got to figure out what 6 times 5 times 4 times 3 is. That's like a 6 factorial minus 2 factorial. So that's 40, so 0.00073. So you basically have a 0.073% chance of all four of them being roses. So the next question says, is either event likely to occur? Yes. I know all the factorials. Factorials is just that number times itself backwards. So like 10 factorials, 10 times 9 times 8 times 7. Like the actual result? No. No, I don't. No. Probably like 4. Like I probably could do it. I just have to think about it because it'd be like the next one multiplied by the next number. Um, it says here that it's likely the bouquet will have at least one rose, but very unlikely that you'll get all four roses. I mean, you have a 64% chance that you'll have at least one, but you have a 0.07% chance that they'll all be that one. So that's basically what they're writing here. So it's more likely to get at least one rose. And that concludes 4-3. I will move 4-4 to next Sunday, but you must get 3-2, 3-4-3 this Sunday, and we'll talk about 4-4 and 4-5 on Monday and Tuesday. Yes, I got you checked in if you want to go see Miss